In this video, we will discuss first-order gradient descent methods for neural network learning. In first-order gradient descent methods, only the first derivative of the loss function with respect to the weights are used. No information about the second-order derivatives are used during the training process. The first-order derivatives are easily available from the backpropagation algorithm. As the name implies, first-order methods work with the first derivative of the loss function with respect to the weights. In other words, first-order methods work with the steepest descent directions. At first sight, it might seem that after backpropagation computes these descent directions, it's only a simple matter of upgrading the weights with the use of these derivatives. However, some modifications are required to the basic form of steepest descent in order to make these methods work well. First, we need to reduce the step sizes with algorithm progression. Second, neural network loss functions often have local optima. So we need a way of modifying the gradient descent so as to best avoid local optima. Third, as we discussed in the previous lecture, widely varying slopes with respect to different weight parameters cause a lot of zigzagging during the gradient descent. So we need a way to address these widely varying slopes with respect to different weight parameters during the gradient descent procedure. So let us first talk about learning rate decay. In the initial learning rate should always be high, but they should reduce over time. The reason for this is that the initial weight parameter is often quite poor, and using a high learning rate is essential in quickly moving to a point in the loss function which is closer to the optimal solution. However, once you near the optimal solution, it is important to reduce the learning rate to avoid bouncing around the optimal solution. The two most common decay functions that are used in this setting are exponential decay and inverse decay. Both of these ways of decay use a parameter k to control the rate of decay. In the exponential decay, alpha t, the learning rate at time t, is defined by an initial learning rate multiplied by the exponentiation of minus kt. In the inverse decay, alpha t is defined by alpha 0 divided by 1 plus kt. So as you can see, in both these cases, as t increases, the value of alpha t reduces with time. In other words, the learning rate decays with time, and the successive step sizes are smaller. Now we note that some gradient descent methods automatically incorporate this type of reduced step size within the algorithm itself, and in those cases decaying the learning rate may not be required. Now the first technique that we will discuss are momentum method. In momentum methods, you can compare the learning to that of a marble rolling down a hill. So here what we do is that we use a friction parameter beta to gain speed in the direction of movement. So the idea here is that as the gradient descent procedure consistently moves in certain direction, it picks up velocity in that direction based on the friction parameter. And based on the velocity picked up, the directions in which it has been moving consistently the velocity tends to increase with time, and the directions in which oscillating movement has been happening, that is zigzagging movement has been happening with time, the velocity tends to be reduced. So let's look at what the updates are. So here you have a vector v which indicates the velocity. So the velocity is defined by, in each step is defined by beta v. So you're multiplying the velocity in the previous step by the friction parameter, which is between 0 and 1, and you're adding the steepest descent value of the velocity, that is the standard minus alpha del L by del W to the velocity. Now note that if you use beta is equal to 0, your velocity is simply minus alpha, the gradient of the loss function, and the step would simply be a standard gradient descent step. However, when you use larger values of beta, you're typically picking up velocity from the previous steps. So you can compare this process to that of a marble rolling down a hill. So this is a very nice physics analogy. So for example, when the gradient descent procedure comes to flat regions, if you use a standard gradient descent, it will slow down in the flat region. And similarly, if you come to a local optima, the gradient descent will get trapped in the local optimum. However, in this case, what happens is that because it has a velocity from the previous movement, it does not slow down as much during the flat regions, and it is often able to avoid local optima. The drawback, of course, is that once it reaches the global optima, sometimes it can oscillate around the global optima because of the momentum. However, this type of oscillation does not lose as much as it gains in getting close to the global optima early. In general, of course, the value of the parameter beta would need to be chosen somewhat judiciously, and that would significantly speed up the procedure. Momentum methods also avoid zigzagging. So here I have shown an example of zigzagging where it shows that with momentum you tend to zigzag more. The reason for this is that if you look at the way in which velocity is picked up, when the directions of movement keep changing with time, what is going to happen is that the velocity in the inconsistent directions is going to reduce and the velocity in the consistent direction is going to increase. So you can see the original way of movement that is shown in B on the upper right is going to get modified to the one on the lower right because the momentum in directions of consistent movement is going to increase with time, and that is why you are going to reach the optimum in a fewer number of steps. Now, there is a very useful modification of the traditional momentum method, which is referred to as an Ester of Momentum. So, in Ester of Momentum, the gradients are computed at a point that would be reached after executing a beta discounted version of the previous step again. So here you can see again the velocity is given by beta v, which is your friction parameter, that is the velocity in the previous step multiplied by the discount of beta, which is based on the friction parameter, minus alpha, the gradient of the loss function with respect to the weight. The only difference really here is that you are computing the gradient of the loss function at a point a little bit further along. That is after you add the momentum component to the weight. Note that in the current update you're going to add beta v anyway. So you add that portion and then you compute the gradient of the loss function. So here what happens is that you have a certain amount of look ahead when you're looking at the gradient. So very often when the marble crosses the bottom of the hill, the directions of the gradients are going to change. So what is going to happen is that just before it reaches the bottom of the hill, it's going to get warned that the direction of the gradient are going to change. And the gradient descent is going to put on the brakes as the marble reaches the bottom of the hill. So there will be less oscillation when you use Ester of Momentum as opposed to the momentum method. Now the Ester of Momentum should always be used with mini-batch stochastic gradient descent with certain modest mini-batch sizes. It should never be used with stochastic gradient descent or very small mini-batch sizes. Now another very popular technique was ADA-grad. ADA-grad uses the aggregate squared magnitude of the ith partial derivative in AI. So one thing that we discussed in the previous lecture was that very often zigzagging happens in gently sloping directions. And consistent direction, the consistent movement happens in gently sloping directions and zigzagging happens in steeply sloping directions. So just to give you an example, here is an example of zigzagging. So you can see along the y direction, the slopes tend to be higher, and what happens is that, but these directions are not consistent. So what you typically want to do is that you want to reduce the velocity in the y direction and you want to increase the velocity in the x direction. And one way of doing it is by using a normalization parameter ai, which is the which is proportional to the root mean square slope along each weight. Now note that here according to equation 15, AI contains the aggregate value of the gradient of loss function with respect to each weight. So if the absolute magnitudes of the gradients are very high in particular directions, the value of AI will be very high. So for example, here the value of AI will tend to be higher in the y direction, it will tend to be smaller in the x directions. And then what you do is that you normalize your gradient descent step by square root of AI. By doing this, you will again be able to get larger steps in the direction of consistent movement, which is like the bottom set of steps, and it will reduce your number of steps. Now, so now there are some disadvantages of using this type of approach. One is that you can see here that the way in which the normalization factor AI is computed, you are using the aggregate of the gradients of the loss with respect to the weight. Now these aggregate values, according to equation 15, they will always increase with time. So with each step, the value of AI will increase. So over time, the sizes of the steps, so you can see equation 16, the size of steps, they are divided by square root of AI. So what's going to happen is that the technique is going to slow down over time. Over time, the step sizes are going to become smaller and smaller, and it is possible for the approach to prematurely slow down and completely stop. The other problem is that the scaling parameter, the AI, it uses tail values. So you can see that in equation 15, we are adding the sum of the squares of the derivative of the loss function with respect to the weights in each step. So after a certain number of steps have been performed, this value of AI is still using something that was added to it many steps back. So that tends to make AI rather stale, and it reduces the quality of the steps that you are taking. So rmsprop addresses both of these problems with the use of exponential smoothing. So in exponential smoothing, you are using a parameter rho, which lies between 0 and 1 for the relative estimation of the gradients. Now, you will note here, this equation 17 here, you should compare it with equation 15. Now you can see that equation 15 for Adagrad is simply takes the sum of squares of the partial derivative. Here you are using exponential averaging. So you are taking the rho AI plus 1 minus rho del L by del Wi square. You can show that by recursively applying this equation, you are essentially taking averages which are discounted using using rho as a geometric factor. So in each iteration, what is going to happen is that the components, the past components of the gradient, they are going to get multiplied by rho. So their contribution is going to drastically reduce with time. The second point is that this is not an aggregation of the values. This is an averaging of the values. And because it's an averaging of the values, the absolute value of AI does not tend to increase with time. So here, now you can see the weight update again, it's very similar. It's identical to what Adagrad uses. So you can see the weight update is, equation 16 is the same as the weight update used in Adagrad. The only difference is that the AI is being computed using exponential smoothing. And in all of these methods, you often add a small amount epsilon to AI to avoid ill conditioning. So the idea is that if AI is very small, by adding a small amount epsilon I, it avoids ill conditioned steps. Then we have rmsprop with Ester of Momentum. So rmsprop with Ester of Momentum combines the Ester of Momentum idea with rmsprop. So again, you have a velocity based on a friction parameter beta I. So your velocity is defined by beta vi, which is you're multiplying the velocity in the previous step with beta, and then you are again adding. So this is your gradient descent step. The normalized the gradient of the loss function with respect to that weight, and after using the normalization factor AI. That normalization factor AI is their rmsprop normalization factor. So the only difference from the Ester of Momentum. So let's look at the Ester of Momentum update. You can see the Ester of Momentum update. The learning rate. The main difference in the learning rate is just using alpha as the learning rate. And here you are adding the rmsprop component by having alpha divided by square root of AI. Now this normalization factor AI, it is also computed a little bit using the look ahead. So you can see this when you are calculating the AI, you multiply rho AI plus 1 minus rho multiplied by the partial derivative of the loss function with respect to Wi, except that this partial derivative is computed using a look ahead. So you're doing it at step W plus beta V. That is because this momentum portion of the velocity is going to get added to the weight vector in the current step anyway. Now, in the book, I have two other methods that are ADA delta and ADAM, and both of these methods, they derive some of their intuition from rmsprop and ADA grad also. So ADA delta keeps track of an exponentially smoothed value of the incremental changes in the weights in previous iteration to decide the parameter specific learning rate. And ADAM, it keeps track of exponentially smoothed gradients from previous iteration in addition to normalizing like rmsprop. And ADAM is actually an extremely popular method, and you can refer to the book for the details of this technique.